Trains look simple: two rails, one engine, one direction. But the real miracle is this: they almost never collide. And that isn't luck. It's a hidden system running every minute, every day. Stay with me, because once you see it, you'll spot the same logic everywhere. Let's start with the obvious problem. Trains can't steer. A car can swerve, a plane can change altitude, a ship can turn wide. A train is locked to the track. If two trains want the same rail, only one can have it. So rail safety is really about permission: who gets access and when. That means the whole network is a coordination problem. You're not just moving trains. You're scheduling access to track. Think of track like a one-lane bridge, stretched for miles. If two trains enter the same space, physics decides the outcome. So control systems exist to prevent that space conflict. Early railroads learned this the hard way. In the beginning, safety was timing and hope. Operators used paper schedules. Crews relied on clocks. And if a train was late, danger grew fast because the schedule was the safety system. When the schedule failed, the system had no brakes. That's why railways obsessed over time. They pushed standardized time and trusted clocks. They used telegraphs. They built dispatching offices. Because if time is your safety tool, everyone must agree what time it is. And everyone must follow it exactly. But timetables weren't enough. Reality doesn't respect timetables. Weather delays trains. Mechanical failures delay trains. Crowded lines delay trains. Once reality diverges, you need live control. That's when the hidden system truly begins. The first major concept is blocks. A railway divides track into sections, called blocks. The rule is simple: only one train is allowed in a block at a time. This is the heart of collision prevention. One train per block prevents most conflicts. So the entire system becomes about controlling entry. If you guarantee one train per block, head-on and rear-end collisions drop. Now, the network is about keeping distance. It's separation, enforced by infrastructure. But separation needs enforcement, and enforcement needs signals. That's why signaling is not decoration, it's control. Signals are traffic lights for steel. Green means go, yellow means prepare, red means stop. Red usually means the next block is occupied or unsafe. It's not a suggestion, it's a command. Early signals were mechanical: semaphores, lamps, and flags. They were visible rules placed along the line. But visibility alone isn't enough. You also need to know where trains are. A human can misreport. A human can fall asleep. A human can lie. So railways needed automatic detection. That required a breakthrough. A car can swerve. A plane can change altitude. Track circuits can turn wide. Modern rail safety possible. The rails become part of an electrical circuit. When a train enters a block, the circuit changes. The system knows the block is occupied. That's huge, because detection becomes automatic. You don't need someone to report, "Train is here." The infrastructure senses it, and the signals respond. Now the safety loop becomes real. Detect a train in the block, then protect the block behind it. Set the signal behind to red. Prevent another train from entering. That's the core logic. Simple, repetitive, and extremely effective. And it works even when humans make mistakes. Now add interlocking. Interlocking controls switches and crossings so routes don't conflict. At junctions, you can't send trains onto crossing paths. One mistake there can be fatal. So interlocking links switches and signals together. If one route is set, conflicting routes lock out. The system refuses unsafe combinations. It literally won't allow them. That's why busy junctions don't explode into chaos. Routes are not chosen casually. They're set like a safe puzzle. If pieces don't fit, the route can't be cleared. You can't accidentally clear two trains into the same crossing. The system blocks it. It turns dangerous geometry into controlled permission. Now zoom out. A rail network isn't just signals, it's dispatching. A central dispatcher manages traffic across large areas. They decide priorities and sequencing. Passenger, freight, maintenance crews, they allocate track time, like air traffic control allocates airspace. Their job is stability. Stability prevents mistakes. Dispatchers use real-time information: where trains are, where delays are, where work is happening. They manage congestion before it becomes conflict. They keep spacing safe and schedules realistic. Because chaos creates pressure. Pressure creates shortcuts. Shortcuts create accidents. So dispatching is risk management in real time. Here's the truth. Rail safety depends on redundancy. One layer is never enough. Signals can fail, humans can fail, equipment can fail. So railways stack layers. One layer catches the failure of another. That stacking is why collisions are rare, not because trains are gentle. One major layer is automatic train protection. If a driver passes a red signal, the system can break. Different countries use different tech. The idea is the same everywhere. Human error is expected, so the system intervenes before error becomes impact. It turns mistakes into near misses instead of disasters. Another layer is speed control. Even with a green signal, speed can still kill. Curves require slower speed. Work zones require slower speed. So systems enforce speed limits in critical areas. They reduce energy and reduce consequences. Because speed turns small errors into catastrophe. Modern networks go further. They use cab signaling, where instructions appear inside the train. The driver sees allowed speed, restrictions, and stop commands. It works better in fog and rain. It's also essential for high-speed rail. At high speed, trackside lights can be missed. So the information moves into the cab. The system goes with the driver. And in many places, there's communication-based train control. Trains report position continuously. The system manages spacing dynamically. It can run more trains with safe separation. It's like moving from fixed blocks to smarter blocks. Still permission, but more precise. More capacity without sacrificing safety. So what's the hidden system that keeps trains from colliding daily? It's not one thing. It's a stack. Blocks, signals, track circuits, interlocking, dispatching, automatic protection, speed enforcement. Each layer exists because something failed before. Every safety rule is written in the ink of accidents. Railways are safe today because they remembered every failure. But the deeper idea is this. Railways turned movement into permission. A train doesn't just go. It is granted authority to occupy track. It is granted access to blocks. It is granted clearance through junctions. It is granted a route, and that route is controlled. That's the same logic behind airports. Planes don't just take off, they receive clearance. They follow corridors. They're separated by rules and managed by controllers. It's the same logic behind shipping lanes, and it's the same logic behind data networks. Access is scheduled, conflicts are prevented, and movement is controlled. So next time you see a train glide past, remember what you're not seeing. You're not seeing invisible blocks, electrical circuits, locked switches, and constant dispatching. You're watching a safety machine, assigning permission every second. And that's why collisions are rare.